Chemistry. This is the start of a new unit on thermochemistry, and this lesson is the Introduction to Thermochemistry. So thermochemistry is the study of heat energy taken into or released by a chemical reaction. All chemical reactions either take in or release heat, so it's an essential part of any chemical reaction. In thermochemistry, we divide a chemical reaction into the system. It's basically the chemical bonds. It's where the reaction is taking place. And the surroundings. That's everything outside of the system. If you put these two together, system and surroundings, that's called the universe. The reason we're interested in the surroundings is the measurements we need to take when we're studying a chemical reaction are from the surroundings. And using those measurements, we can determine what's going on inside the chemical bonds, inside the reaction. So you'll see how that works later on. So the change in energy, delta E, equals the work done on a system plus the heat absorbed by the system. Delta E equals Q, heat, plus W, work. Alternately, negative delta E is work done by the system on the surroundings plus heat energy released by the system. So if we think of a car, all energy, the gasoline, produces work, that's making the car move, and heat, wasted energy. So we put in the gasoline, that's the total energy, and part of that goes into making the car move, and part of that, in fact most of it, goes into heat or wasted energy. Work requires movement against a force. If the only force against a chemical reaction is the pressure of the atmosphere, then no work is done. And virtually all the chemical reactions we do are simply open air. They're against atmosphere, they're open to the atmosphere, and so no work is done. This means that a constant atmospheric pressure, the equation reduces to delta E equals Q, equals the heat. There's no work done, there's nothing being moved. Heat taken in or released by a chemical reaction at constant pressure is called a change in enthalpy, and that's delta H. So basically delta H is the heat. The enthalpy is the heat of a chemical reaction. It's the best way to define it. For the rest of this course, heat entering or leaving a chemical reaction will be represented by delta H and represents the change in energy delta E of the reaction. Positive delta H represents heat entering a chemical reaction. Negative delta H represents heat exiting a chemical reaction. For the rest of this course, heat entering or leaving a chemical reaction will be represented by delta H. An endothermic process is when heat enters the reaction and is shown as a positive value delta H. So just think of endo as sounds like in. It's going in. Heat is going in. An exothermic process is when the heat leaves the reaction and is shown as a negative value, negative delta H. So it's like exit. It's exiting the reaction. Remember that money into your bank account is positive and money withdrawn from your bank account is negative. So heat going into the reaction is positive, heat coming out of the reaction is negative. Heat leaving the reaction system equals the heat entering the surroundings. So negative Q, heat of the system, equals positive Q of the surroundings. They're just equal and opposite numbers. The reason we need to know that is because we can't measure what's going on inside the chemical bonds, but we can measure what's going on in the surroundings, as you're going to see, and so we measure the surroundings, and from that we can determine what energy came out of the chemical bonds. So temperature is the average kinetic energy of the molecules. This translates to meaning that higher temperature increases the speed of the molecules. So temperature is measured in Kelvin or centigrade. So if you have two identical molecules and one is heated up, it's going to move faster. So we can think of temperature as being a measure of the speed of the particles or molecules. So temperature is the average kinetic energy of the molecules. This translates into meaning that higher temperature increases the speed of the molecules. Temperature is measured in Kelvin or centigrade. So there you see two molecules moving at different speeds. One is a higher temperature than the other. But if you can put a thermal conductor in between the two like that, then eventually they equalize. And that's called thermal equilibrium. Here's another example, a summary of the difference between temperature and heat. So here are two identical blocks at two different temperatures, and now what we're going to do is put a thermal conductor between them. That could either be a duct like a pipe, or it could be simply a piece of metal. Metal will conduct heat very well. So you're going to go ahead and allow those two to reach an equilibrium. You can see the one on the left is becoming cooler and the one on the right is becoming warmer, and they're going to continue, assuming that none of the heat can escape into the atmosphere. We're going to assume that they're going to continue this process until they reach thermal equilibrium, and there it is right there. The temperatures equalize at 350. So here's the key of the definitions. Temperature is the internal kinetic energy of particles in an object. So if that's a solid block, then those atoms in there are wiggling, and that's their kinetic energy. Heat is the transfer of thermal energy between two objects of different temperatures. So just think of temperature as being internal to the object and heat as being external. It's a transfer of energy between two objects. There are many kinds of energy, mechanical, such as throwing a ball, electromagnetic, sound, light, heat, and others. For our purposes, the only kind of energy involved in a chemical reaction is heat energy. Now later on we're going to learn about an ultimate type of energy called free energy, but you don't need to worry about that at this time. That doesn't exist as far as we're concerned. So key points. For a chemical reaction, that is making a new substance, okay, the heat energy absorbed or released in a chemical reaction is the same as the energy stored or released from the chemical bonds of the reactants and products. So that's chemical bonds, creating new substances. For a physical reaction, that's just simply change of state from solid to liquid to gas. The heat energy absorbed or released by the chemical reaction is the same as the energy stored or released from the intermolecular forces of the solid, liquid, or gas. In a chemical reaction, heat energy delta H must enter the reactants to break them apart, and heat energy delta H must be released from products to allow them to form into products. That's true whether it's an endothermic or exothermic reaction. Heat has to enter any chemical reaction. That does not make it endothermic. And heat has to be released from any chemical reaction to make it form into products. That does not make it exothermic. It's the difference between those two amounts of energy that will determine endo and exothermic, and we'll see that in a minute. So energy in to break reactants on the 2H2 plus O2, you break those into atoms and they reform into two water molecules. That's energy out to form products. In a physical reaction, energy must enter the substance to move from solid to liquid to gas, and energy must be released from the substance to move from gas to liquid to solid. So there you see energy in to melt the ice to water, and energy out to freeze water back into ice. A potential energy diagram graphically shows the beginning energy of the reactants and the final energy of the products, and the energy path between the reactants and the products. So if we look at point B, that's the initial energy of the reactants. They already have some energy. On the vertical axis, we have potential energy, and on the horizontal axis, we simply could measure it in time or something else, but basically it's moving from left to right there. So the initial energy of the reactants is point B. Then C is called the activation energy. Activation energy is the energy required to break the reactants. So it's the difference between the energy that the reactants already have at point B and what they need to have way up there at point A in order to break apart the reactants into individual atoms. This is called the activated complex. That's point A. The activated complex is where all the reactants are broken into individual atoms. Now they're ready to recombine to form products. Then D, the downward slope, is where the energy is released to form products until it reaches its final energy at point D. So energy goes in to break the reactants apart, and energy comes out to make them form back into products. And the difference between those two levels, it's the final minus the initial. So that would be D minus B. That's going to tell you what the energy difference is, and that's going to determine whether it's endothermic or exothermic. So an exothermic reaction occurs, that's when the heat comes out, when the sum of the energy in to break the reactant bonds and the energy out to form the product bonds is a negative delta H. Energy is released from the overall reaction. So if you take D, level D, down lower, and level A, subtract from it level A, you're going to get a negative number. Okay, so that's a negative delta H. So point B, this is the activation energy. The activation energy required to break the reactants into individual atoms. C is the activated complex. This is where all the reactants are broken into individual atoms. Now they're ready to recombine into products. And D, the downward slope, is where the energy is released to form products until it reaches the final energy at point D. Point E is the difference between the initial and final energy, it's final minus initial, of the reaction. This is a negative delta H for an exothermic reaction. So delta H equals the potential energy final minus potential energy initial. An endothermic reaction occurs when the sum of the energy in to break the reactant bonds and the energy out to form the product bonds is positive. So that's positive delta H. Energy enters the overall reaction. So all chemical reactions take in energy to break the bonds of the reactants. That's the upward slope on the left. And release energy to form bonds of the products. That's the downward slope on the right side of the curve. Point E, in an endothermic reaction, the final energy of the products is greater than the initial energy of the reactants. This is positive delta H for an endothermic reaction. Specific heat is a measure of how much heat a substance will gain or lose when the temperature changes. Specific heat is specific to each substance. Water has a specific heat of 4.18 joules per gram centigrade. The formula for the relation between heat and temperature is given by this. So this is a key formula. You're definitely going to use this on the AP exam. Q, heat, equals the mass of the substance, that's in grams, times the specific heat. For water, you see it up above there, times the change in temperature. So basically, Q is heat, M is mass, C is the specific heat of the substance, and delta T is the change in temperature. The units of measure for energy are joules, pronounced joules, or calories. In this case, it's joules, 4.18 joules per gram centigrade. The units of measure for energy are joules or calories. A calorie, spelled with a lowercase c, is defined as the amount of heat required to raise 1 gram of water 1 degree Kelvin. So it's an amount of heat. A kilocalorie, spelled with a capital C, is 1,000 calories and is the number used for food products. So 250 calories, spelled with a capital C, on a small bag of Doritos are kilocalories. So this is 250,000 lowercase c calories that we use in chemistry. So 1 calorie, the equation is 1 calorie equals 4.19 joules. The advantage of using joules is that it is the same kind of energy used for light, mechanical, electrical, all other forms of energy. So let's give an example here. Water has a specific heat of 4.18 joules per gram centigrade, and iron has a specific heat of 0.45 joules per gram centigrade. How much will the temperature of each substance change if 2,000 joules of heat energy from the sun is absorbed by each substance using 50 grams of mass for each? So think about this. You take a cup of water at 7 a.m. in the morning and you put it out next to iron railing. And you let it sit for 10 minutes, and when you come back, you touch the railing, it's very cold. Early in the morning, the railing is cold. The water is kind of cool. It's not super cold, but it's kind of cool. Now you come back at 2 in the afternoon, 7 hours later, and you touch the cup of water, and it's gotten a little bit warmer, but it's certainly not hot. And you touch the railing now, it might be so hot you can't even touch it. It's gotten really hot. That metal railing's gotten really hot. So let's see how that works in this equation here based on the specific heat of iron and of water. So first solve the equation Q equals MC delta T for delta T. And this gives delta T equals Q over MC. So now we're going to plug in the numbers. For water, it's 2,000 joules. It's the same amount of energy both the iron and the water received from the sun. over 50 grams, the mass over the specific heat, and that gives you a 10-degree increase in temperature of the water. Not very much. It's a little bit warmer, but not much. Now what about the iron? So iron, it's 2,000 joules also, 50 grams also, but look at the specific heat. It's much smaller. So that's a 90-degree increase in the temperature. So that's why the iron goes from being very cold to very hot, even though it took in the same amount of heat energy as the water did. The water didn't change its temperature very much. So this explains why on a cold morning an iron bar will be cold and water will be cool. Later in the hot afternoon sun, the iron will be hot and the water will be warm. The higher specific heat of water means it can absorb a lot of heat without changing temperature much. All right, and that takes care of this introduction to thermochemistry lesson.